sure. Stuff is really
Hey, he's my favorite person. You guys suck. I got, that just reminds me, I gotta go get water.
Yeah, that might be more for like, I guess flying is and robots and devices that will track. So maybe there's
market right now. They're using it a lot for materials, and so they're working jointly with NASA for a lot of just making the high strength materials like plastic.
okay.
And they've also been working with some oil companies like Chevron, where there's lots of stuff like artificially vibrating pipes that
Raise itself in 24 hours.
vibrating pipes that
Jeffrey just wants to pick up his vodka bottle.
Yeah, really.
There's something about a vodka bottle, or water bottle, I can't understand it.
Downstream.
Share with the class, Jeffrey.
The main problem is getting smart materials that
I keep so few 2 hours go by, and so that's not a terrible thing.
Yeah, but so much money for it.
Have you seen the equation? They go years.
Don't feel bad, like, I'm sure you had, more of it too than I did.
Really?
Yeah. I mean, I took pictures for you right here. Actually, pretty much everyone here was. So you did I still.
Okay.
So, we're in the same boat.
Yeah.
Thank God.
I'm actually doing.
Yeah, I
Is this grad school, is it because of undergrad?
No,
Too
absolutely
intense
not.
for me?
No. Because that trade was intense.
No, that just was crazy.
Yeah, I mean, so this don't feel bad. Like, when you said
No, I mean,
something,
I
you don't
understand
understand it,
it.
I'm probably like
That's gonna
10 steps behind you. So.
That's good.
I'm on red flag in here. What's your opinion?
I thought you were saying you're 10 to behind me. That's what I said. Hey, Omar, come on, that's not cool.
No.
Now it's like 3,000.
I'm not a dick. I can also plan.
They're hearing you and watching this.
It's fine.
Okay.
How's it going?
It's on desert.
Yeah, exactly.
Did we even touch one, well, probably one or two equations yet?
What?
This one?
Yeah,
Versus testing?
he mentioned something, but I don't know how the test is gonna be. We should probably ask him that, because I feel like if there's a test on anything he's been going over, I don't, it's done. I understand.
Yeah, I've heard it. Like Wednesday. Really? She got into Thanksgiving week. I don't know how it's product.
Is there a problem? No, I thought you knew, but that was very example.
And so I'm really and that's all about putting the ground help to water.
He did say that he's just gonna consider only the basics and then quantify it.
We need to ask him about that. Make sure you don't get basics.
So far, there hasn't been basic.
Hey, Jeffrey, is that vodka?
We thought you said vodka bottle.
There was class, man. Water bottle. Oh,
That's a
man.
lot of vodka for one guy.
Yeah.
Hard hitter.
Okay.
That makes it last, right?
So yeah, Jeffrey's gonna get a job on the rig.
Yeah.
Oh yeah.
Welcome to the roughneck.
Because I
Welcome
just
to the
love
marathon.
gigantic white people. Because I just love those. Gigantic white people who want to beat the shit out of me. Yeah, I love those.
Even what?
Yeah.
Big-
You can't get enough of those. You know, I just haven't gotten put into the trash can enough.
Probably.
You know, that was an experience that I should you know, and that has always made me sad. You know? Yeah.
I hear you. But I don't hear you, I have no idea what you're talking about. Cause I am.
I just want to go into this order again right now. Well, and try to remember what that was. I'll go to the bottom of that. I don't know what it was.
Jaeger bomb. That's what it was. For Jaeger bomb. Good time. Yeah, that's incredible.
What's incredible?
You know what a Jaeger bomb is? Jaeger and, Red Bull?
No. Red Bull, yeah.
Well, there's a friend of ours, he's an engineer, and also a connoisseur of liquor, and he's never had that drink before, and that's like, first, if you drink, the first thing people tend to gravitate towards or as far as we were amazed. Interesting.
So interesting. Almost as interesting as
paint drawing? Can we just like try to open a door and
no, it's air pressure from opening the stairs. Because
gotcha.
Yeah.
Positive pressure ventilation. Hey, did you know that all stairwells are ventilated as per code that are over 4 stories tall? That's why you feel like kind of like a breeze in the stairwell. Life safety.
Yeah, the more you know. Yeah, the more you know. Which makes it dangerous if there is ever a chemical attack.
Oh no, that's the point of having ventilation, and it actually blows any smoke or whatever contaminant away from the oxygen. It's actually sucking in there.
Well, you know why they started the fire at the ground in GM? Apparently the poker chip firm, and they had
Formaldehyde?
I don't know, for whatever the chip, and then it went up to the top floor and poisoned everyone.
Holy crap. Yeah. No, that's the downside. If you have like a fire at the ground.
I would laugh. Rich people back in the day were evil. So.
They're not evil, just really like gambling.
Apparently the people on the top floor survived.
Good for them. Well, they paid for it too. You pay for the top floor, you pay for your life, right? Yeah. In that case. Maybe. That sucks. Vegas. Who wants to go to Vegas?
We don't have enough money to gamble away in Vegas. Yeah. It's not fun if you don't have cash.
Yeah, that's true. Well, how about
if you don't have money, it ain't fun.
That's true. You don't have money to give away.
Yeah. Or they don't like you. So it's not.
True.
Like, unless you're a group of really hot girls who just go there and get that paid by somebody who wants photos.
Pay the girls? What? You thought that was right?
No, I've no, like, hey, we're from SoCal. We know girls who get paid to go to Vegas and just party there.
They're called.
Yeah. Huh? No, you don't have to. The hotels will actually pay like really pretty girls to go there and just hang out at the pool. I don't know about that activity, but I know they. I know that.
Whenever you put so much thought into this.
Like,
so what? Did you have an option of petroleum? If that doesn't work out.
Yeah, there you go. Hey, that's the oldest profession, right?
Hey, if I had an option, because I make so much money, if I had an option, I would not. if I could get away with
You
it.
would not be a hooker?
I would not be a hooker in any way ever, but.
Really?
I'm
disappointed in you, Jeff. Oh, man, that's not right, man.
Depends on how happy Rachel lady is, actually.
Oh, yeah.
Like,
Good point.
it depends on what she's offering and how much.
Jeffrey's going for
What's on the table?
What's on the table? What is being offered at the moment?
Just on Craigslist.
Yeah, Craigslist, they have the casual meeting toys. Professor. I went up to your office to see if you were there.
Yeah, no, I had a carryover meeting that was now instead of, what it's supposed to be, sorry about that. I sort of figure if that's all I have to do in this life, is do a meeting. Yeah, I did not get a chance to, order pizza. Who knows how to do that? What do you guys want?
Pepperoni.
Okay, so there's 12 people, 4 and 4. Does anybody need a vegetarian?
That would be good.
Yeah, okay.
The guy who can't eat pork.
He can't eat anything.
Not on the, 4 hours. Jesus. 4 hours.
Go order. You pay for it, and I'll take it back.
Our favorite.
Is that okay?
Yep.
You sure?
Mm-hmm.
I will have 10 minutes. Okay. I apologize, I'm still in the meeting I ran out of. I had to tell them finally, let me go. You don't want to be in a policy meeting.
Just 4 pepperonis, right? Large.
My man, he has to have vegetarian.
Yeah. Oh, right, yeah, him. Okay, you don't mind if it's like half?
Yeah, that's all right.
Like, what I mean, half and like.
Why don't you just do
one?
Do one.
Okay.
Yeah.
Just around trees, something.
And don't cut corners, order whatever everybody wants. Anybody want meat lovers?
Okay.
Yeah. They look like they want meat lovers. This is not complicated. Dennis, go with it. Come on.
You're not gonna cover anything important, right?
Yes, I'm gonna talk about you. Okay, so we talked earlier about some of the things that are issues with planning and execution, and this is where I was in talking about that, the preparation of the well for actually performing the testing. The production history, as I mentioned, is not trivial. If you start having shut-ins and that sort of thing, it will contaminate your test data, and you need to be really careful about that. How many of you, we're kind of starting fresh, and you may have forgotten this, but how many of you recall what I said would happen is that they would shut in the well to put the gauge in, or to put a tubing carrier in, or that sort of thing, and then you turn the well back on for 1 day, and then shut it in for a month. You've corrupted the test. It isn't going to do what you want it to do. So, make sure they understand that. And believe me, field people will do what you design under most circumstances. But if you leave them to their own devices, you will regret it. I had a young student, or actually a fantastic undergraduate student who contacted me and said, hey, look, my company's running a pressure buildup test on this well, and this, that, and the other. And I said, you must run a downhole shut-in device. It was tight gas, only gas, very high pressure, very high temperature. And he just ignored it. And they ran a bottom hole gauge, but with no downhole shut-in. It was 11 days long, and the whole thing was corrupted. And he was like, why can't I analyze it? I said, because the whole data set is corrupted. It's in wellbore storage, and it will be for the next 6 months, because you did not run a downhole shut-in device. And that was a difficult conversation to have, because you just wasted 11 days. Go ahead.
Does downhole shut-in,
It's a wireline conveyed, like a wireline packer, which the gauge carrier is below. It's expensive.
does it solve the problem of the bubbles that you talked about?
It would if you had a packer. If you don't have a packer, it will U-tube around the back and do the same thing. But, you know, I want to be careful what I say, because if you have fluids on top of the packer that aren't bled off, or on top of the device that aren't bled off, it could conceivably cause it to leak, I suppose. But I would assume that if you have downhole shut-in, and your configuration is that you have a packer at the bottom and you're shut in, then you're pretty much isolated. But if you don't have a packer, which a lot of wells do not have a packer, there's a variety of reasons why, not the least of which they don't want to get the packer caught anywhere near the curve. They try to put the tubing as low as they can in a horizontal well, and if they go running with a packer, it could get caught. And, I mean, you can figure it out yourself, but that would be another trip, drill it out, blah, blah, blah. So I'm finding that part of the problem is the construction. But if they're above the curve, they should definitely have a packer in a horizontal well. But this was a normal hydraulically fractured, relatively modest perm, probably 0.05, something on that order, low permeability, but not ultra low. And the reason that it didn't work is it was very high pressure, high temperature gas, and there was no facility for isolation. So this was going to bleed itself off slowly into the formation for the next 3 months. The well completion, I've told you this before, have the records in hand, make sure they're available.
Veggie piece of man, what do you want on it?
Sorry?
There's like lots of options.
Okay.
Man, just go ahead with anything. Go ahead with anything. Not a problem.
You're very kind. I was almost sent you out with him.
Oh. Thank you for not
But
doing
then I'll
that.
be lecturing to the clock. Because then the next person will have to go, and the next person. All right, why are you testing the well? This is the most important question. And if you don't believe this is going to happen, you are going to be asked by someone, why are you doing it? A few weeks ago, I was asked to attend an online webinar on a new system that actually has the ability to measure rate and pressure down a horizontal. Okay? So in theory, it should be a continuous production log, you should get pressure measurements, you should get rate measurements. Theoretically, it looks fantastic. It's a series of components that have been used for something else. It's not a major service vendor, but of course they would like to be, and will get purchased by a major service vendor, and all get rich, blah, blah, blah. First question somebody's going to ask, why do you need this? What's this going to do for me? What's your answer going to be?
You can measure you can do the test without shutting the well.
Okay, but why would you put a 15-station rate measurement system in a horizontal well in the lab? Do you know how much hardware and jewelry that is? You're going to have wireline conductor all the way to the surface. You're going to have 15 different gauges and these sensors along with the fiber optic that's in the cable. What's this going to do for you? You know, I'm an academic, I can't answer that question. I can tell you a lot of people have run production logs in long horizontal, trying to understand, and maybe that would be part of it. Do you guys know the rule of unintended consequences? You ever heard this before? Never? Okay. There's always unintended consequences. When you borrow money from your parents, they think they own an unintended consequence. Okay? Can you think of other unintended consequences? Let's say that I decide that I'm going to change a policy in the department, and it's going to seem perfectly logical to everyone. But then it has an unintended consequence of causing you to have to stay here an extra semester. We just didn't see it. We didn't factor it in. You know, anytime you have a system which is functioning and you stick something else in it, there will be a consequence to sticking something in it. The one thing that I saw with this is that it reduces the bore size by all of that hardware in there, but that actually might help. because the biggest problem we have in horizontal wells is unloading them. So if you reduce the diameter, you'll increase the velocity, and conceivably that could help. It could backfire on you. Why? With all that stuff in the hole, what happens if you start having sand and pieces of rock or junk fall in behind these packers? You'll never get the system out. And instead of renting it for $5,000 a day, you just bought it for $5 million. I'm exaggerating, but there's always something to do that. And I was trying to explain to someone how things work in the oil field the other day, and how the multi-stage horizontal frac system for the frac point system works. They use balls. Okay, so it's a very complicated system, but it's actuated with different sizes of balls. So it's a fail-safe. It should work. Obviously, the balls get bigger as you go up. So the person I was explaining to just had their jaw drop. They were like, "That's really simple." Yeah, because it's 3 miles down, and you don't have any mechanism to operate it. So it has to be simple. But in theory, you could lose a ball or get one stuck in the wrong spot, and then bad things will happen. But of course, they engineered that into the system. So why are you testing the well? What is the objective that you have? If you say that you're testing a well to get the permeability, I want you to watch carefully out the corner of your eye, because you're about to be hit with a book or a stapler or a paperweight or something. No manager cares what the permeability is. They have no desire to know that. What do they desire to know? How can this well be better? That's the question they want to know. So you can use the permeability to model it, and obviously to make other scenarios about how you would maybe change the completion, that sort of thing. What about fracture efficiency? All wells now in lower permeability systems are hydraulically fractured. Doing some diagnostics on that would be a good idea. No one's going to test a well to estimate reservoir volume, because that's just going to take too long. Now, on the other hand, you may want to leave a gauge in a well forever, and it's not that expensive to do it. People think it is, but it's not. There's this dark light contraption that can be dropped, a gauge configuration. And it'll last for 90 days. You can pull it back out, download it, put it back in. I know you're going, well, you missed an hour or two of data. I understand. But, beautiful data, missing an hour, beautiful data, you can live with that, or whatever it is. It's not expensive. So something like that may be a system that people could use to permanently monitor. What would the value of permanently monitoring be? Pressure is your bank. Whenever you don't understand where it's going or what it's doing, that's like your bank account. And once it's gone, it's gone. We don't have any more. And systems where we lose pressure and we didn't get production because of it, we're going to have to do something else. Usually some sort of stimulation treatment, perhaps, but if the pressure's gone, it's gone. We may have to use injection systems. Just think about why you want to run a well test. Now maybe you're saying, look, old man, you've gotten beat up a lot, people have asked you for what to do, and you always gave them your best answer, and they yelled at you because they don't want to run pressure transient tests because they're expensive, they have to be designed, they have to be implemented, somebody has to monitor it, somebody has to champion it. Someone has to be the person who says, I'm going to watch this, I'm going to sit on it, I'm going to make sure everything goes okay. So when I was a little bit older than you, I said, why don't we invent something that gets rid of pressure transient tests? And why don't we do production data analysis? So instead of having all this stuff, we just monitor production and did the same thing. And that'll be next week, but that was the logic behind it. Okay. The difference is pressure transient testing provides you with something that production analysis doesn't. It provides you with a snapshot of what's happening right now. Permeability shouldn't really change, but the condition of the well can change. And that's why, if you're thinking about, can I use production data analysis to estimate the same things that I would pressure transient? Yeah. But pressure transient analysis gives you almost the ability to interrogate the reservoir. Now, if you have a downhole pressure system, then basically production data analysis and pressure transient analysis are one and the same, because the reservoir doesn't know the difference. You can take the data and process it however you want. But I just want you to realize you've got to have your objective in order when you want to run a pressure transient test. Monitoring is primarily for alarms. People measure an enormous amount of production data for alarms on pressure and for sales on rates. And then they stop measuring water and it drives you crazy. But for pressure transient analysis, everything you do is a cost. There's a cost to the equipment, there's a cost to the time that the well's shut in, there's a cost to the personnel who are going to have to monitor it. And their logic, management's logic is, what am I getting for this? Now, what about, they call it opportunity buildups or opportunity shut-ins. When you guys did platform maintenance, there you go. You just plan yourself around that, and you drop a gauge in before you do platform maintenance, and you've got a, there are wells that are being completed right now in shales. They're completed and tested. You've only got a 30-day window, at least in Texas, to test. I don't know what it is in Pennsylvania, but you guys probably don't realize that Pennsylvania is mountainous. It's doesn't have a lot of good roads, et cetera, et cetera. There's no pipeline, per se. So they drill the wells, they complete them, they test them, and then they sit there for 3 months, 6 months, 9 months, a year, waiting for the pipeline to get filled. Okay? There's a perfect opportunity to monitor pressure. Of course, you're out in the middle of nowhere and there's no production, so what are you monitoring? Pretty much nothing. You could use that to get a background read on what pressure's doing. You could use that to sort of see if your wells are interfering with each other during the shut-in period. When shale first started, companies needed to drill leases to hold them. Pretty much still true, but most of it's drilled up, or at least we've got a footprint somewhere. I'm not saying they're I can think of play X that has 16,000 well locations left, play Y that has 50,000 well locations left, and so on and so forth. But they know where the resource is. They've drilled wells pretty much all over the place. So holding things is not really a primary goal now, but there may not be facilities there. Comparison of pressure transient analysis, production data analysis. Pressure transient is high resolution, high frequency data, so that's the good stuff. Okay. In Thailand, do you have real Coca-Cola and local Coca-Cola?
Yeah.
Which one do you prefer?
Well, the local was it, I don't think it's doing it anymore, but I like the red one.
You like the real one?
Yeah.
Okay. So that would be your preferred product, but you got to pay extra for it because it's made by somebody outside the country or that sort of thing. So whenever you're thinking of PTA data, it's got to be high quality. It's going to be expensive. There's going to be a cost associated with it. Okay, and like I mentioned, it gives you a snapshot of the well performance. It gives you some idea of the well efficiency at that point. Production data analysis, or PA, production analysis, is low resolution, low frequency data. It's passive monitoring. In the past, on some of the videos, you'll see where I did an example of this. I take your pulse. Taking your pulse is passive monitoring. Okay? But then if I pretend to let you go to sleep, and then I, pretend to be a psycho killer with a pickaxe, your pulse is going to shoot up. It's a stress test. So that a pressure transient test is some sort of stress on the system. Production analysis is just continuous monitoring. So basically, whenever a system is stressed, it gives a different signature than when it's not stressed. And that's why we perform pressure transient analysis. Okay, so this is actually 30 years old, actually a little more, but it's almost exactly accurate to what we would be looking at today. Not a lot of things have changed since then. Okay, so in this case, you have a seal assembly here, so there's a wire line, comes down through here, and you have a gauge, but this is sealed off. Okay? So being sealed like that means hopefully that we don't see too much pressure come up. But this one over here actually has a valve in it that isolates the bottom. You've got packers in both. And this is more or less what one might use on a drill pin test. Okay, so the gauges here are in carriers, they're memory gauges. They can run sometimes up to 90 days on batteries. This isn't drawn to scale. How do you think you're going to have enough batteries to run these gauges for that long? Have you seen these battery assemblies? They come in 10-foot lengths, so they just keep stacking them onto each other, just like you would a giant flashlight. You know, just keep screwing them together to get more power out of them. There are some new technologies for generating power downhole. I worked on a few of them. They never came to anything on my watch, but I understand that a company has developed a technique for putting a current through the wellbore, through the casing, and through the tubing, which isn't going to be a very efficient connection because the tubing's hitting the casing all the way down, but they claim they get enough power to run things. There's all sorts of, ideas, I guess I should say, like a turbine of some sort that would power a battery. There's some smart materials that have been tried that would generate electricity from thermo changes. But for the most part, we're stuck with batteries. So, and like I say, if you use batteries carefully, you could probably be down 80, 90 days. Now, they're not on continuously. They've got a smart system that puts it to sleep and wakes it up to pick up measurements. Okay. All right. So this is an example of a DSP. Does anyone know who Barnum and Bellow work for? No? You got your thingy? Yes. They work for Exxon. Okay. And so Exxon has a formula for everything. If a light bulb goes out in Jakarta, there's a book in Houston that tells how to change it. I'm sure everybody who's listening to this is laughing, and then they're going to turn me into the Exxon police, but it's true. So they have a a DSP sequence, and you can see here that they open the well. Why did they open the well? For only a short period of time, isn't it? Mechanical engineer?
Yeah, mechanical.
Okay. This is the original pressure in the mud column. Okay. They've got to get the mud off the gauges. So they open the well to flush it out. And the first thing that you notice happens, you can't see it, but the pressure drops immediately down to there. And then, of course, it's shut in. Right. Shut in. So then the pressure builds back up. Like that. Okay. And then they do it again. And you'll notice they put a dashed line here because they don't really know what it is, because they're looking at the drawdown here. The drawdown goes doo, 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 doo. So they just sort of drew this in as a cartoon. You're not supposed to tell them when they said that, though. All right? And so then they shut it in again, and the pressure comes up and over like this. Now, Jeffrey, you ready? This line, or this maximum pressure right here, what is that? That's the initial reservoir pressure. And then they flow the well for an extended period of time, and then they shut it in again. Okay, so here's the flow data. And again, they're using dash lines because they're not sure exactly, and it kind of bobbles around and that sort of thing. And then they shut it in. See, these are those rates I was telling you about. They're blocky. These are days. So that's, each one of these marks represents a day. So it's like they're reporting a daily rate here, 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 like that. Okay? How much is Exxon worth?
Okay. I thought it said it's from August 3rd to August 4th or something.
Oh, sorry, it's every hour. My mistake. Sorry. Thank you.
$100?
No.
465? Or 365?
What does it say, the price is right?
Total market cap. Total market cap.
Oh, wow, you're pretty good. Did you know that?
Yeah.
How much does Cisco worth?
200?
136. Cisco is supposed to be the first $1 trillion company. How much is Toyota worth? 200. How much is General Motors worth?
Holy shit.
Hey, watch your mouth on this phone here, boy. Yeah, there was a time whenever Toyota could have wrote a check for General Motors during the bailout, and, that would have been the end of that discussion. I know, leave politics out of the bedroom. All right, sorry, I meant every hour. My mistake. Thank you very much, Sam 1. Okay? So then they shut it in again, and here we go. Now, Jeffrey, why did I draw it like that? I drew it as though it was not going all the way back up, but in fact it does go all the way back up, right? Why? Because we only produced it for how long, Sam? Since you can count better than me, 12 hours? 11 hours. So from here to here. That's not 11, that's 9, sorry.
24 to 7. 11.
No. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I can count. That's 11. Sorry. Yes.
Might have mentioned this, but where did the 100 psi come from again? The one on the 16th, on hour 16 on August 3rd, the very initial point?
Here?
Yeah.
This is the mud column.
Oh, okay. I get it.
Okay? So what's happened is we've got a well bore full of mud, and obviously to keep the well from flowing, so we have to flush it out. Good question. All right. So what do you expect to get out of a 11-hour test?
Well, more storage.
Okay. One thing we did get was we got an estimate of average reservoir or background reservoir pressure. So that's a biggie. And the way that had been working in the past is they always did a two-step production sequence. They would produce it to get the mud off, to get initial pressure, and then they would produce it to get an estimate of near well transmissibility. That's what Exxon called it. Exxon had its own formulation for this. I would have thought that they would have produced it a bit longer than that. It looks like it's only for an hour, but I would have thought they would have produced it for a little bit longer than that to get an estimate of near well transmissibility, which is here. This is the data that would be used for that. Okay? Now we could try to digitize this and use this, but they made the point so big it's going to be garbage. I'm going to shoot it, so I wouldn't bother. Okay? And then we have the extended production period and the extended shut-in period. And the extended, in this case, has an interesting connotation because it's 11 hours, a little bit more than 11 hours. Most tests will be run quite a bit longer. Of course, it is a DSC.
Does it not give us the full pressure curve though?
Sorry?
does it not give us the full pressure curve, like that shape that we're used to when we're living?
Oh, you mean over here? Yes, this should be what you're talking about. That should be the normal buildup.
And what about the first, they add until two as
These two?
pressure test?
I think the first one's probably gonna be contaminated, and I mean that by, it's basically an impulse. It has a very short production period, followed by something that looks like, 3 to 4 times as long. The theory behind well testing really favors a constant rate, a long duration constant rate, and the shorter the rate period is relative to the buildup, the more messed up it'll be. The buildup will reflect that. Okay, here's Schlumberger. I see, Joe. I'll come to you in a second. Who wants to work for Schlumberger, right? Okay, so the Schlumberger, if you go back and read Joseph Ayud, who's really a bright, decent fellow, he wrote a paper called Impulse Testing. It's essentially a homework problem. I mean, we could sit down, a hard one, but, you know, graduate school homework problem. We could sit down and we could write a paper on impulse testing, maybe not as crisp and clean as he did, but nonetheless. Impulse testing was, you took a volume of fluid out of the reservoir very quickly, and then you watched the pressure dissipate, okay, or build up, however you want to think about it. What's wrong with that?
Not practical.
Anybody else?
Are you referring to like?
What's not practical?
You can't just grasp the pressure wave will advance at...
Don't say wave. Pressure
I'm sorry, the pressure distribution will advance at the speed of sound, but your fluid, the rate in which you're taking out the fluid is much
Okay,
slower.
your logic is right, but I'm not sure about all of the elements of practical. What he's trying to say is an impulse means that the fluid is withdrawn from the reservoir instantaneously, and that cannot happen. So there is a finite period of time. Maybe it's 10 minutes, maybe it's 5 minutes, but somehow you take a surge of fluid out of the reservoir, and then you watch the pressure pulse. Pulse is a bad word, but in a sense that is a pulse. You watch the pressure distribution propagate, okay? What's wrong with that? All of our well test analysis theory is set up for a constant drawdown at a prolonged rate with a fixed shut-in point. All of our theory is relative to that. Now, we can handle any variation of that, especially modern software. If you take that impulse test and put it in modern software, it's going to drive you crazy, because that impulse test is going to use that very short production period. It's going to put it in the superposition calculation that modifies all the x-axes on all the graphs, and it's just going to look meaningless. I bet. Maybe I'm wrong, but I bet. Okay. Also, what would you expect to get from an impulse test? You said that the speed of propagation was controlled by something. Okay. What's the number one thing that the speed of propagation is controlled by?
Permeability?
Correct. So can we estimate permeability? Maybe. Permeability is going to be scaled as a square root related to time for that kind of calculation, and there may even be an exponential term because it is so early. It's an impulse. You have to look at it. So the reason that people went to this was because they wanted to try to sell a service where they would do this. They would pull some volume of fluid, I don't know how much, maybe a few dozen barrels or a few barrels, and then they would watch the pressure. In theory, good idea. In practice, okay, let me rephrase this. If you were going to design an impulse, think carefully. How would you do it? Dennis first, and then Jeff. Or were you not raising your hand?
The only thing I can think of is just the shut-in where you get into a steady state of drawing constant flow rate, then you suddenly stop the flow rate.
That's a good idea.
That's the only way.
That's actually a very practical thing as well, but it could take hours to do that. Is what you're
But
saying.
that's the only way I can see to do an impulse with that system.
Okay, but that's not an impulse, because it's a prolonged period of production.
But that's the closest to an impulse I can see.
How about it? Yes.
Well, the direct delta can be an instantaneous decline or an instantaneous increase. So,
Okay.
shove 12 barrels of liquid into
And
the.
who's been doing that for the last 100 years? The water resources people. What do they call it? They call it slug testing. When you drop 12 barrels into the well, does it happen instantaneously? That's the problem. Neither way does it work perfectly. So you end up with this artifact due to how you're trying to represent an impulse. My feeling is it's probably got some application, probably some usefulness, but I wouldn't bother with it as a common practice. I think it'd be too hard to. I don't know that it'd give you what you want. I mean, here is the closest thing you're ever going to see to an impulse. Right here. And then it's recovery. But remember, the only way we can analyze this is to have some sort of a model tied to it. Okay. All right, we'll leave that. Okay, now this is straight out of the Schlumberger book. Oh, by the way, why would Schlumberger do that again? They want self-service. They pushed the impulse test and they pushed the multi-layer test. Actually, that was Dr. Economides' baby. I don't know whether it was her idea or something she ended up on, but late 80s, they were really pushing multi-layer testing. How do you do multi-layer testing? Single-layer testing is obvious. Everything comes out of one zone. Multi-layer is going to be more difficult, right?
Yeah, some isolate them by factors.
That would end up being multiple single layers. And you're right, that would be doable. But what if you're going to try to do them all at once?
Multiple heights into the wellbore.
Now, you would use a device to check the flow rate coming out of each zone. That was their desire, was to use a spinner tool, which is kind of like a pedal, basket full of pedals and turn. What's wrong with that? These things are notoriously inaccurate. And I know they say they're to this percent or that percent. We already had this talk about what errors do to deconvolution. They'll have an effect with convolution. If you're looking at 20% error, you've got a mess on your hands. You're going to end up with something that doesn't tend to a solution. Okay, so let's talk about Schlumberger's book now. And what you're looking at is the first case, and this is, as he points out, skin, no storage. And why is this a straight line? Dennis, do you remember? Delta T is equal to a function of the exponential integral. Remember that? That I got. Sorry?
Yeah, I did it.
Okay. It's also equal to a function of the logarithm of time. Distance doesn't matter because we're at the wellbore. Good thing you reminded me of that. Thank you. And what else? It's going to be proportional to permeability. Okay, so permeability is going to be there. Some other stuff as well. Okay. So the concept of the skin factor is that these two profiles have different. They're located at different points, and so their point is that there's no. There is a skin, but there's no wellbore storage, so there's no distortion here. Here, there's wellbore storage, but there's no skin, so you see that. And then here is skin plus, wellbore storage. Okay. So this is the ideal solution with no skin. This is the ideal solution with no storage. What's the one thing that you notice that doesn't change on these two plots?
The maximum pressure of the reservoir, the initial pressure.
Good point, hadn't thought of that.
Go back again.
Look at what in,
I think infinite acting radial flow.
okay? Very good, Jeffrey gets a gold star. I know he wants to be special, so. Okay. So what is that proportional to? The slope, M, is proportional to permeability. Okay? So the permeability is dictated by the slope of the line on a semi-log plot. Remember, this is a logarithmic scale. Now, practical question. You need to pick a pressure drop such that you can calculate the skin factor. Where's the best place, pardon me, to select a pressure drop? If pressure is equal to a function of time, what location on this plot is going to be a nice fixed point? Actually, I misspoke. It's not a function of time. It's a function of what kind of time. Pressure is equal to a function of the logarithm of time. Correct? On this plot, what's the most convenient location to pick? Sorry? 1. Why?
The log equals to 0.
Exactly. So the pressure at time equals 1 hour is how we are going. We don't have to. It can be a total generalization, but we're going to fix that point as what? As our reference for calculating the skin factor. Okay? There's a lot of detail left in that, but that's the point we're going to fix. So we're going to read it off of here or here, one or the other. Okay? The pressure at 1 hour. You're going to hear this talked about a lot. Pressure at 1 hour, pressure at 1 hour. Okay? It's affected by the skin. And we chose it as a convenient point. Do you select the pressure at 1 hour from the data function or from the model? The straight line. Yes, again. It's all relative to the model. Okay. All right. What's this out here? Boundary dominated flow. Okay? We already said, are we going to see this? Probably not. If you see boundary dominated flow after 10 hours, how big is your reservoir? It's either really small or the permeability is astronomical. What's astronomical? Like 10 Darcy's. Okay. Would it be helpful to have another function? And why? Would it be helpful to have a function that tells us when the slope is constant? Yeah? Can we formulate a derivative that will do that? What is that derivative going to look like? So let's say that y is equal to a plus b log, or log x, okay? Is that all right? I'm using natural log so I can be lazy. Okay, so what is dy dt? Or dy dt? Yeah. What's the derivative of a constant?
0. And b over t.
And that's going to be b over x, or t, sorry. right? D over T, sorry. That's not constant, is it? Let's multiply both sides by T. So the derivative function we're going to define is going to be T, dy dt, and it's going to be equal to B, your definition. Okay. What do you think of that? Okay. So now the question is, how do you calculate this derivative function?
Yeah, at the time you have the differential pressure, you can do it numerically with the point.
Okay? Is that easy or hard? It's easy. But if you calculate this with a point-to-point difference in Excel, what are you going to get? Okay, you're doing sort of oscillations, or you're doing random.
No, instead of having something like that, you're gonna have.
Okay. So when we apply it to real data, which has normal variations in it, what are we going to get? Okay, I'll make it really simple. What happens when you take a derivative of a cloud? You get a much bigger cloud. Okay. So if you have any error in your data, probably, and I mean random error, probably the derivative function is going to be a little iffy. So what do? Well, that's what I was telling you yesterday, is you or the day before, is you reformulate the derivative. How do you reformulate the derivative? You reform it as some sort of a weighting function, a simplified function. Now, could you conceivably fit an equation to this data and then differentiate the equation and calculate the derivative that way? Yes, and that's how one vendor used to do it. What happens when you use an equation? Then you're going to get oscillations. It's just going to wiggle and wobble and that sort of thing. Right, so we need a pressure derivative function. Ta-da! There's a pressure derivative function. Okay. So here's the wellbore storage trend. Unfortunately, they didn't draw it through the actual data. I can do that. What's the slope of this line? Okay, so it's 1 to 1. So delta P is equal to some constant times
Long.
delta T, right? Isn't that what it is here? Okay. And then this derivative is calculated how at these points? T times dp dt. Okay. And they've drawn in a nice flat spot out here. So there's your radial flow effect. Yes.
A qualitative question. Do you, this method was developed for vertical wells. Do you think they'll redefine a vortex derivative for horizontal?
You know, the simple answer is no, but the truth is there are horizontal well derivative functions. But what people have decided to use, kind of like using the dollar, they're going to go ahead and use a radial formulation for that because they don't want to have to convert everything to something else. And the radial derivative formulation, it just is a coincidence. This derivative formulation where you're looking at y prime equal to x dy dx. Oh, so they, you didn't pay for it yet? Here.
No, credit card.
Are you sure? Here, I got cash. Can you break 100? No.
I already paid it with credit card.
Oh, did you? Can you break 100?
Probably not.
That's good for me. I'm just lying. All right. So there's the definition of the derivative. It has no intrinsic connection to radial flow other than for the radial flow case that yields a constant. Jeffrey.
Oh, right, yeah, everybody wants to.
And we don't wanna let you, fall behind. You might have to retake the course. How many of you'd like to see Jeffrey retake the course? I got 3 nose scratches, and a couple of people pretending to comb their hair. Okay, somebody tell me what this is.
Oh, that's the French scarf thing you said you were gonna bring.
I've had it for over 30 years.
Wow.
So it's ordered on.
Here, you can touch it if you want. Okay. So the derivative function has exactly the same character as the pressure function over here, and it's flat over here. Does everybody see why? All right, we're going to repeat Jeffrey's favorite love song from the 70s.
Let's do it again.
All right, here we go. You guys need plates and napkins, right? I'll go take care of that. You brought your own.
Well,
All right. Jeffrey, you can finish the lecture. I'll be right back.
What? Let's see how much I remember from King.
Probably not.
Yep, nothing.
Yeah, you were there? Yeah, you were there. Sat next to me.
That was my final.
Yep. Okay. What would Dr. King do?
You're making me feel bad, come back here.
I don't remember what kings do. How much percentage is for pizza boy? Like a test for pizza boy? I went for a restaurant percentage. Yeah, I went for a restaurant percentage. I was like, oh, okay. Wait. See how much I saved percentage wise. Tip calculator. No, almost 15. Damn, I'm generous.
For delivery boy, is thinking money just because they have the gas as well.
Well, he's gone, and he was saying thank you too. So
No, you didn't say that time checking.
I think I gave him 8. Pretty sure. I mean, that's why I don't like cash. You're never 100%.
You're not supposed to give it in cash, but just mention it in the.
Here, do some construction terms.
Tip amount.
Oh,
Why did you have to do it?
I didn't do that right.
Which that was that?
Before saying the thing, yeah.
I mean, I'm just guessing it was all of them, but you hate me.
That's okay.
Oh, God.
Hmm? All right. So over here, we have delta P is equal to M wellbore storage times time. Over here, we have delta P is equal to some constant, which we can call delta P 1 hour, plus n semi-log times the logarithm of time. Okay? And what's going to happen there is we want to take the derivative of these two equations. The derivative function delta P prime is respect to time, and that is a prime. So that's delta P prime, okay? That's our definition. What is the derivative d by dt of m wellbore storage times T? It's m wellbore storage, okay? And then when we multiply that by time, what do we get?
Volume.
That gives us m wellbore storage. And then when we multiply both sides by T, that's delta P prime. Okay? So delta P prime is also equal to what?
M wellbore storage.
M wellbore storage times T. And this is called the wellbore storage domination. You guys like that word, right? Domination. Okay? Dennis, you cool with all this? So we have this area of the data that is dictated by these equations. Again, these guys didn't draw this very well. But the line, the unit slope line, go through the data. Stop moving. I didn't draw that very well, did I? You know what they say, Jeffrey? Every bad carpenter blames his tools. This is your ruler. Okay, so this applies here. Now what you'll see me doing a lot in the old assignments is I draw these barber poles. Where does this regime end? Where does it end? It ends where these two split apart. Okay? Because then the derivative and the original function are no longer the same. So what I like to do is I like to put a barber pole there. You guys know barber poles? Jeffrey, when's the last time you saw a barber?
About 2 weeks.
Really? I couldn't tell. Hippie. Is it true you're going to do study abroad, Jeffrey? All right. So that's the wellbore storage domination region. And these are the models which represent it. We have delta P for the M wellbore storage times T, delta P prime equal to M wellbore storage times T, right? Everybody good with that?
Yeah.
Okay. So, we have delta P is equal to delta P 1 hour, which is a constant, obviously, plus MSL times the log of T. Does anybody remember the conversion of log of T to log of T? So log of T is equal to what? ln of T divided by what?
ln of 10.
ln of 10. That's the base conversion, right? Sorry?
I think it's 2.7 something.
I think it's
Yeah, right.
No, I think I was just thinking about the value, it's 2 point something.
Yeah.
Yes, yes.
So if I want to write this in terms of, do I have it back?
No.
It's all right. I always get confused when I do difficult things. All right? So we have now delta P is equal to delta P 1 hour plus natural log of 10 times MSL times ln of 10. Is that right? Correct? Okay, so that means that this is delta P prime is going to equal to, take the derivative, multiply the derivative by time. What's the derivative of a constant?
Zero.
Okay? And then plus the natural log of 10 times MSL times what? The derivative of log of t, dt, multiplied by t. So that goes to 0. And that leaves us with natural log of 10 times MSL times what? What's the natural log of t, derivative?
1 over t.
Okay, so that's just,
Times t.
that just becomes 1. Okay? So this t times the log of t dt is just equal to 1. Okay, so delta p prime is just this. Okay. I really hope this is right. I can't remember. Yes, it is.
When you derive it right there.
No, I know it is. I'm thinking in my head. It's been a while, eh? Okay? All right, so where does radial flow start? It starts where this becomes horizontal, because that's what this says. This says delta p prime is equal to natural log of 10 times MSL. MSL is on the previous page, okay? So we got to make another barber pole. Now, the question is, how generous do you want to be with the barber pole? Do you want to be conservative and come up to here? Or do you want to be a liberal democrat?
For this one, you probably should be conservative because we're at the later end of the.
So you're saying we should push it to the far right so that we can be conservative?
Yeah, sure.
It's a regime that gets better with time, so we want to push it to the right a bit. Okay? All right, so this location is actually related to what? What's this height related to?
P1 over is.
No. What controls the height of this line?
Yeah.
How good your data is.
This is proportional to permeability. Okay? This is proportional to wellbore volume. All right? We'll talk about the real equations some other time. Actually, you'll probably do that on your own. The distance from this trend to this trend is indicative of, related to, somehow calculated with the skin factor. Okay? Jeffrey, go ahead.
I'm sorry. Which line were you referring to when you were asking about what you answered to be permeability?
The height of this line right here, the red line, or I can make it blue.
So does that,
The location vertically of that line is only dependent on permeability. Okay?
I thought.
That's how it relates to the semi-log plot on the previous page. Okay. Anything else? No?
When you say related to, proportional to volume of wellbore, is it the length of the?
No, it's the M wellbore storage. I'm going to butcher this. I need to look it up. I think it's equal to. I'm going to screw this up no matter what I do. Okay, I'll take a guess. It's QB over 24 CS. I think. Yeah. Okay. CS is proportional to the wellbore storage coefficient. Or sorry, it is the wellbore storage coefficient. It's proportional to wellbore volume. All right. Have you guys looked at my Petty 324 stuff yet? Okay, I'm going to lose this, so everybody make a mental image. Yes, no? How's that vegetarian?
It's good.
Yeah? The other night I had chili paneer. You know it. Yeah, you can give me the receipt. Tell me the number. 72 bucks? The hell, man? Let me see that.
I actually mistakenly gave him $8 in cash too, for tip, and I wrote.
Good God, I ain't never letting you buy anything.
In that case, I'll get another piece of pizza.
How much cash you got? You got another 20? No, doesn't matter. You can go. I got enough for the 20. Sorry. Okay, has everybody got this? Man, you're worse a money spender than my wife. Give me a heart attack. Okay, so you come over here. How'd I do that? The course archive, Petty 324, 09 is fine, reference is fine, course notes is fine, pressure transient solutions, these are the fundamentals here. This is how you derive the solution from the diffusivity equation. Okay, I'm not going to bother with that. And then these are the fundamental solutions that are derived from that. So then it's 620 to start with, then convert the equations back to their sort of other form. And you've got this whole derivation explaining where the relationships come from, how they're calculated, what the formulation looks like, etc. Okay? All the equations, if you want, are here. This is what I was telling you a moment ago. This is the definition of this. Okay? We just did this, right? Only I have it backwards. How did I do that? Do I have it backwards? Yeah. How did I do that? We had it upside down again.
You had it
Yeah. Oh. You know, it's free, so. And then the next one is for buildup. And you derive all the equations here for buildup. This is all by hand. And you can derive variable rate buildup, single rate buildup, and so on. Again, all this really is to orient you. And you have the pressure buildup analysis sheet, and here's all the equations for calculating things with this. Sorry about getting that term upside down. There's an example that's all worked out. So here's the wellbore storage effect. Here's the line that pours through it. Here's the horizontal radial flow trends. This is a data set that's sort of a simulation. It's actually taken out of a series of text. So let's come back to this. We had our barber pole here and here, correct? We have an equation for wellbore storage over here. We have an equation for radial flow over here. What do we have in the middle?
Transition.
Nothing. We don't have a transition equation. Okay? This is a teaching moment. Everybody ready? Wellbore storage means wellbore only. The only thing we're getting out of this is the properties of the wellbore. In particular, what properties? The volume, which is here. All right? How valuable is that to you? It's not. You already know the volume of the wellbore. Okay? This becomes what? It's like a signpost. Wellbore storage. Okay? There's no reservoir value from this point. Yes?
It can't, although it can be tested, it used to test hole integrity, right?
You know, in theory, that's probably not a bad idea, but the equations, while they're rigorous, the information that you put into them isn't, and the likelihood of coming up with the correct wellbore volume, I mean, you'll be close, but it's not going to be, if I ask you to calculate the wellbore volume from the data trend, we usually don't calculate the wellbore volume, we calculate the wellbore storage coefficient from which you could calculate the wellbore volume. That's more of the parameter we're interested in. Wellbore storage coefficient, what are the units? Reservoir barrel per PSI. So it's a volume over pressure terminology. You could then put in all the information because you're going to have a compressibility and you're going to have a volume. You could back solve it for that. But depending on what the compressibility is, depending on this, depending on that, let me put it another way. I've never done it. But I don't think you're going to get an answer. If the volume of the wellbore is 87 barrels, you're probably going to get something between 60 and 120, you know, or 60 and 105 or something like that. It's not going to be a calculation that you would use to validate. Now, I do believe I have asked people in the past, like on an exam, to calculate the wellbore storage from the theoretical equation, which is in the book. And whatever equations you need, I'll probably give you on the exam because I don't want you fumbling around and making mistakes and that sort of thing. But that particular equation is probably not going to get you on top of each other, just so you know. All right? So there's no equation for the center. The equation, or the information on the left is the wellbore. And then what's the equation on the right, or what do we get out of the equation on the right? We have a well, let's say in an infinite acting system. The wellbore comes down, looks like this. We can see the radial flow lines. They're coming in like this. They convergent radial flow like this. What equation describes that? We already went through it. It's the pressure and the logarithm of time. Okay? So what do we get from radial flow? We get permeability, and we can use this to estimate the skin factor. Okay? All right. So what do we get from the wellbore storage region related to the reservoir? Nothing. What do we get from the transition region? Nothing. Is anybody disappointed yet? Okay. Welcome to reservoir engineering. So the moneymaker part of this plot is where?
After 10 hours.
And this is an idealized example. Definitely high permeability. There's no value in that data. I'll teach you, you'll learn, blah, 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 you'll make calculations, but there's no reservoir value in that data. So So if you could, what would you like to do? If you could, exactly, you would like to move this hump, or you'd like to remove this hump over to here. All right? And of course, that pressure trim is going to be like that when you do that, okay? But that ain't going to happen.
You said in
Downhole shut-in.
We can use downhole shut-ins, but it's not going to totally eliminate wellbore storage. That, I mean, what I'm really trying to do is be exaggerated and say, you're never going to not have wellbore storage. You're going to always have some. Boy, double negative. Somebody go back to school for that one. Okay. Questions or concerns?
what we usually use this as like a flag to say, let's say, okay, this, we have to experience this first. So
Right, and what we'll do when we actually give examples of analyses and so forth is we use that as a guidepost. You know, I always describe wellbore storage as a tax. You may not like it, but at least you know where you are. And there is no reservoir information going to be derived from it, but at least you know you have a signature before you can see something. But you're conceptually correct. You're not going to get very far with wellbore storage. And I didn't draw this exactly correctly. This is going to come over here. And this is going to form its own straight line. Okay. If you could have an equation that would model the transition, what would that equation be a function of? Think carefully before answering.
It would have to do with fluid flow and flow regime.
Okay, be specific.
Viscosity.
Oh, sorry, I didn't mean fundamentals. I was trying to get you to explain that such an equation would have to have a wellbore part and a radial flow part. Okay, let me rephrase it. Is there a universal formulation? No. It won't work that way. There's not going to be an equation where you can reverse into whatever part of it you want. And the reason is because wellbore storage is an implicit rate change. I told you it's reservoir barrels per PSI, so it's actually a rate as well. We already went over that, I guess, on Monday. It'd be nice if we had such an equation. Any ideas on how you create it? No?
You weight the two functions.
Trying to remember if I had it in here. Yeah. Okay, so this is an approximate form of the wellbore storage concept for radial flow. It's not an equation that you can use. This is the behavior in the Laplace domain. So this is the overall relationship. Dennis is the only one who's going to understand that. And then this is an approximation that can be derived for wellbore storage. This is the solution that governs the reservoir, and this is a multiplicative solution that represents the wellbore. And then there's another formulation of this that has the solution and its derivative, as well as the storage component. Does everyone see what would happen if you had a function like this? No? What's going to happen? Okay, but what's going to happen is this particular function will model wellbore storage over here transition over here.
Exponential.
Correct. There's an exponential decay term from what would be this extrapolation into what would be that one. Okay. But it is not accurate enough to use something like that. I just wanted to point out that it's there if you wanted to try it. Sorry, your old man should have gotten more sleep last night. At least I didn't sleep in the car driving down. Okay, so this is a build-up plot. Why is it plotted backwards? These guys need to get out in the real world for a while.
Because it's a
The
border
plotting,
plot.
it's a Horner plot, but it's plotted backwards. How would you fix it? What's the easiest way to fix it, Bill? Do the Excel thing and make the min and max, just switch them, make it flip. Yeah, that's the easiest thing to do. You can always tell when somebody makes a build-up plot going the wrong direction, that it's their first time or something like that. It's okay, it's still just as accurate. But what will happen is this is extremely early time based on Horner time. See, this is a big number, this is a small number, so this is a large number. And then as you get over to here, it drives the logarithm, it drives to 1, and the logarithm of that is 0. So we would start here, we would work our way up. This is the actual data. It gets on the line and keeps going. That's the cartoonish nature of it. Here's the time at 1 hour, which is determined by looking at the axis, and then you read it off the model, not off the data. Okay? One of the things that you need to do whenever you're performing well test analysis is once you stare at it long enough, and once you put the model on there, you need to mentally strip the data off. The data is no longer part of the process. The model is. All of these equations reference the data or the model. The data or the model. They reference the model. They are the model. So when you start drawing straight lines on here, when you start taking points and moving things around and calculating slopes, you're talking about the model, not the data. Okay? In your mind, once you put a line on there, just peel the data off the page, because you don't have the data anymore. You're dealing with the model. The model is the equation.
Why is it not affected by skin?
The buildup, that's a really good question. That's a really good question.
Please repeat the question.
He said, why is it not dependent on skin? Can I throw a lifeline? You know Lifeline? X Factor, Survivor, whatever, what the hell is it called? What uses a lifeline?
Think who wants to be a millionaire?
Yeah. I want to see if Sam One would give me a hand. Okay, so who can I throw a lifeline to? This is a hard crowd, It's kind of hoping for a little more love and understanding, but just came to the wrong place.
$1 million question.
What, you want to do it the easy way or the hard way?
Hard way is good.
You got the terms for skin factor?
Sorry?
The rate.
Let's do the mouse. Okay, so here's the cartoon. Okay? Pressure buildup test. The data start over here and work their way over to there. It's plotted from 10 to the 4th to 10 to the 0. Scrolling up, the equation that we had for the buildup is where? Okay, so we're going to just keep working our way down, 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 down. Okay, I'm on the wrong one, sorry. Okay. So we take two equations, take the first one and the second one, and there is a skin term here, right? What's the skin term multiplied by? 0. Okay? So it effectively knocks, the plotting function effectively knocks the skin factor out. All right? The final equation looks like this. That's the equation of the straight line. There's no skin factor term. Why? Because the 0 rate knocked it out. You see, now you want to put it back in. You want an equation with skin. Where is the last piece of information that has skin?
Before you shut in,
Perfect. Keep talking.
you have the...
So instead of referencing initial pressure and shut-in pressure, what are we going to reference? The last pressure in the drawdown. Because that pressure, the last pressure in the drawdown, has a skin factor in it, right? So now we reformulate the problem. And you can see what I'm trying to do. Exactly like what you just said. So it does not include the skin factor. So now I'm going to reformulate. I'm going to solve for pressure minus the flowing pressure, which does have the skin in it. I'm going to select that behavior at the total producing time, TP. Okay. So I've got this equation that has skin in it, and you'll notice it's reference to initial pressure minus the flowing bottom hole pressure at this time. This is a single value, correct?
If a delta T equals 0 on that,
Okay.
not
This is a constant. All of this is a constant. Does everybody understand that? The pressure drop at delta T equals 0 is dictated by that equation. It's taken at time equals TP. So that is the last drawdown pressure. So it has what? It has skin. Okay? So then we take that and we combine it with the other buildup equation, and look what happens. We take it and combine it with the equation that doesn't have skin. Where the hell is my mouse? Okay. And what we end up with is a new plotting function for the x-axis. And we end up with this. Let's pick on someone other than Jeffrey. What are the units of this new plotting function?
The time unit T.
Right. It's time multiplied by time squared, divided by time, so it's time. So what do we call this? We call it effective time. We've actually known about this equation for quite a while, because this is how we originally formulated the pressure buildup formulation back in the 50s. But a fellow by the name of Ron Argwal, who did his PhD here, worked on this problem late in the 1970s. He wrote 2 papers that should never been published. Okay? And this was one of them. This was the effective time.
Why never published?
It's really hard to explain, but it just wasn't something people wanted to see. You know, it's there were people that said it was too simple. We recently had a publication that was turned down that we performed, you know, an excruciating amount of work to prove that a simple concept wouldn't work. And we actually had a technical editor write us a letter back saying, I appreciate all the work you did, but it's obvious that this would never have worked, no matter what. No. You don't get that. You know, the reason we did the work was to prove it didn't work. All right? And you're going, okay, what the hell problem are you talking about? let's say, instead of drilling a horizontal well with multiple fractures, you want to create something else. There's a person out there who has said that he's going to create a device that will use a horizontal well, and it will cut a slot in the reservoir, like how you cut rocks in a quarry. You run a cable through it and it cuts it. Never been done, never been demonstrated. I'm sure the Russians patented it because the Russians patented everything. This guy has this idea, that's fine. And so the code advisor and I were talking about, what kind of problem would be interesting. The fracture, or the slot, is going to be at least this wide. From your education, is a fracture this wide going to be a big producer?
No.
This wide?
A fracture? Yeah.
Yes.
Okay,
It's going to be huge. And that was the guy's logic, was that if he could have this device and it would cut a slot that was 1/2 inch to 3/4 inch wide, then this thing would be a gargantuan producer, right? Will it produce the same as or better a horizontal multi-frac well?
I think it'd be worse because the permeability of the formation around it is still the same. You have
Correct,
drainage.
but you have a huge cross-sectional area and you have absolutely no pressure drop due to that fracture, or that slot. But your intuition is correct, and that's what the technical editor was saying. He was saying there's no way this will ever compete with a horizontal multi-frac well. Why? Because a horizontal multi-frac well would have a lot more cross-sectional area. Duh! We know that, but we still wanted to prove it. And guess what? The slot drill does have a regime where a 1/2 inch wide fracture or slot, when you first open the well, the rate is like infinity, it's but it immediately drops to a low number. We had to program the living daylights out of this, a numerical solution. This was not a trivial undertaking. And after, like I said, we presented it, we did this, we did that, and then the editor says, this is not an interesting problem. Okay, not an interesting problem. Well, the same thing happened to Aquawall here. People said this has been done since the 50s, but nobody ever said, take this quantity and make it a plotting function. This actually, equation 18, was part of the formulation. It was the base formulation for how you obtain the skin factor from a buildup test. And nobody ever stopped to say, well, why don't we plot this? Because what this is, what equation 18 is, an equivalent drawdown test. Right? If I plot delta P here against that function, this looks, smells, tastes it is exactly the same form as the drawdown equation. So he called it effective time. And it made a buildup equivalent to a drawdown, which in theory was supposed to do what? Make buildup analysis independent of producing time. This is like one of the biggest steps in well test analysis ever. At the time this came out, people were generating curves with multiple values of TP because they didn't see that it would normalize itself out. So you would see a curve that had all these TP values on it because, as I told you all day, TP is the producing time. It has an effect on the performance. Whatever the value of TP is, you can't ignore it because it has an effect. But if you create this effective time thing, it normalizes all that out. So the process now is to always plot buildups with effective time. Okay? So Agarwal gave us that. He also gave us something called pseudo time. And before you have a cow, pseudo time is like pseudo pressure. It's to correct the nonlinearity. Okay? Both of these were tremendous adds to the literature. Look up the paper on this effective time by Agarwal, and you'll see some of the written equations were handwritten and that sort of thing. I think that really made them crazy when they reviewed it. But, well, not the whole equation, but pieces and parts. Anyway, there's your equation for estimating the skin factor for buildup. You use the drawdown pressure, the last drawdown pressure. Yes, on top.
So this proves it's mathematically. Could you tell us, like, physically why
buildup is not affected by skin like.
It's easy because the mathematics nulls it out. The equation that we get for the Horner equation, it just knocks it out. It isn't there. I know what you're saying. This is very confusing because the data plot hasn't changed. What has changed is which equation we're using.
Right.
Okay? But the Horner plot, the one that doesn't have skin factor in it, all it tells you is how to interpret what? The so-called semi-log straight line. This. Okay? That does not have skin factor in it. This is the equation for a buildup. You have the initial pressure of the system. You have the shut-in pressure of the system. You have all this. Okay, I see what you really want me to tell you. Do you see it yet? It's reference to initial pressure. When the reference is initial pressure, there will be no skin in this equation. So what we did was essentially reverse this, and the reference is now the last drawdown pressure. Okay? So delta P here is PI minus PWS. Delta P down there is PWS minus PWF at shut-in. We changed the reference. And by changing the reference, we put the skin factor back in. But as far as the plot you're looking at, it's still the same. This is an interpretation mechanism. And I know people are going to say, but the plots aren't the same. What I'm trying to say is the Horner plot has its trajectory. The effective time plot has its trajectory. They all have a semi-log straight line. They all have a point where you can interpret something. You can use this formulation, the Horner formulation, Cp plus delta P over delta T. You can put that on the x-axis, and you can make this calculation. But then what you would do is you would come back, and you would use the solution that's here for the skin factor. This skin factor equation is valid for everything. Why? Because it references pressure at time equal. The pressure is shut. So quickly I'll go to a cartoon and explain all this again. Okay, so in this case, it is a logarithmic graph. The axis here is dP plus delta T over delta T. This is a Horner plot. The axis here is the shut-in pressure. So down here, this is very early time, this is very late time. The individual points are here. And then we draw in the trend. Straight line, I believe it was equation 18. Okay. So there's equation 18. So the slope of this line right here, only that part, is the part we're looking for. Now, they went on to tell you where T1 hour is. They use meters for it. So P1 hour is here. Okay. That's a TT plus 1 divided by 1. So you just look that up on the grid and store it. You calculate the slope. How do you calculate the slope on a semi-log axis, people? What's the easy way? You take this point, and you're going ahead and take this point. How many log cycles are there? 1, 2, 3, 4. This pressure difference divided by 4 log cycles. So whatever this delta P is. So MSL is equal to delta P divided by 4. Okay. For this plot. It won't always be 4. You'll have to decide yourself. Does that make sense? Everybody's happy with that? Okay. Remind me again, what do we get out of wellbore storage? Well, on this plot? Nothing. X it out. Alright? But you'll notice that in this particular case, the pressure at 1 hour is in this wellbore storage region. But it's not taken from the wellbore storage data, it's taken from the straight line extrapolation. Does everybody understand that? It says nothing, one does not have anything to do with the other. Once you put this model on the graph, you forget about the data points. In your mind, strip them out. Okay. P star. P star is approximately initial pressure in an infinite system. When I say approximately, it is the initial pressure in an infinite system. All right, then we also have a drift over the P bar. The question that I've asked you over and over again is, are you ever going to see this? No. Nobody's going to shut in a well long enough to see that.
What's the difference between P bar and P star be determined?
It's basically the depletion. Good idea. Good point. Okay? Now, there's a methodology by Matthews, Bronze, Haysbrook that is formulated as P star minus P bar. It's very, very clever. What they did is they figured out how to represent P star by P bar, or P star and P bar. Okay? What's the problem with it?
It's not going to be very accurate.
Because
You
can estimate P star, and then you can go to the graph and you can reverse calculate P bar. But you have to know what? You have to know the entire production history. Like I said, it's dependent on depletion. So you have to know the whole time, you have to know the volume that was produced. If you know all that, you know the answer anyway. It's a very clever approach, though. Is there a graphical way of predicting P-bar? Yes. Is it particularly useful? No. It's a derivative methodology. I can demonstrate it to you some other time, but it does work. It's just not, you're not going to see enough data to make it work. Step out of this for a while. And Daddy needs an energy drink break. Okay, while I'm going to go get myself a drink, would you study this and tell me what it means when I get back? You guys don't look very happy. Make sure we put the boxes outside in the hall or throw them in the dumpster when we leave.
There's a whole piece of left, guys. Sorry again.
I remember something.
Yeah, from Reservoir, that's the only
I'm not
thing.
sure I remember.
We just go down to like few small points.
Yeah, this is clergy. I don't know what the second, it's the second infinite acting radio flow is,
You remember how he had a curve, well, and then curve, and then go straight down.
Well, yeah, we have this, but what happened?
oh yeah, that's the slope doubling?
Yeah.
Oh, okay.
So it means like the one on the well.
That's boundary.
The boundary flow?
Yeah, when you
Yeah,
have
but
double
what, right?
flow, 180 degree boundary.
Is it when you have like an impermeable boundary?
Yeah. Well, the degree you multiply depends on the angle.
Okay, yeah, that's right.
If it was one wall, you double. If you use two particles, something like that.
Yeah, and we could examine that out of the equation.
Not even darker flow.
I remember I got like a 40 or something on that.
Not even dark.
We have to calculate the floor. We didn't have
We have to derivate it.
Okay, and now, so guys, since I absolutely paid that guy $80 more because I wanted, I will be taking the rest of the pizza. And since Laughing Game doesn't want it, so I get it.
Go for it.
Pay for it. It'll piss it off.
Like, whoever wants vegetarian pizza can have it, because I don't.
No, it's fine. I can use peaches. There's dessert. Last call, taking this box.
That's all for alcohol? I'm good, thank you.
Box, no. Alright, go to my office.
Did you make that?
Yeah.
Really? What is it? Wow, that's good, man.
I'll take a
If
try.
I wasn't fasting, I would have some, so thank you.
But you can eat when the sun goes down, right?
Yeah.
So when you finish at the age, you should be able to.
Be able to eat. Yeah, they
8:25 is sunset.
every day, look at that, that calendar.
I did it for once.
Yeah. It's like hell the first 2 days, so your body gets used to it, and then it's fine.
I did it one day, like, stayed around the clock. I must have got the rest of the day.
Yeah. When you do that? So you keep that $8 to the guy? Last game gave him $80.
Oh, it's fine, okay. It's covered.
He's good.
I mean, unless I drink in a bar, it's more than $8 sometimes.
Yeah.
I know, that's ridiculous.
That's ridiculous, huh?
I already got Domino's, not Pizza Hut.
Yeah, same here.
I bet they charge them like $20 for delivery too.
It's probably like $2. But I think he just topped it off with everything he loves in the world.
That's pepperoni, that's the cheapest pizza.
It's only pepperoni and vegetarian.
Really?
Yeah.
Wow.
Pizza Hut is overpriced.
I was, if I was the Laughing Game, I would just like,
Okay, hell no, I'm not paying for that.
put that one in the truck. I mean, pizza.
You ever made a now I did feel like making it.
Yeah, that's the reason I didn't want to eat, but
How's your summer going so far?
Summer. What do you mean?
What summer? More like time of when stuff we're gonna eat.
I'm throw away trash.
What year are you at?
Sorry?
Which year?
Fourth. Fifth.
Who are you working with?
Not yet. I don't know what.
Okay, one last thing.
I don't know what's happening yet. What I'm just taking engineering or not taking. I don't know.
ME or MS?
Okay, then last veggie pizzas over there.
I'm done with my master's program studying, but I can come back sometime in 5 years to figure it out. So I don't know if I'm gonna do a job or I have a bachelor's or I'm gonna continue my school.
Yeah, the option. Yeah, not there, just 1 year.
Yeah, it's still awesome.
I'll tell you for me, because trust me, working then going back to school is like really go.
Did you give me budget? Did you give me individual prices?
I just said, okay, 3 pepperoni and
That's why they have this column that's called special.
Online thing when it's Domino's wouldn't have delivery. The bill works on the online. Sometimes it's not there, and then Pizza Hut wouldn't recognize the address.
Stop guessing, Tim.
Why did you
My daughter's name is Jean.
Yeah, did you go with I believe 1950s children, the council policy?
No, my daughter's named after my mother.
Oh. Okay.
Who are you named after?
Well, Jeffrey's just something that my dad thought would be nice.
Can I rename you?
George Michael. I did not think that. I actually looked him up. His song is pretty famous. Apparently.
I need to get out of here.
Michael Blues? No, I don't think so.
Okay, so this is a chart that explains what the different plots are used for and how they're used to make estimates of property. You'll read from the column down, the Cartesian plot here is used to work with wellbore storage. Square to time plot is here, it's used to estimate fracture property. 4 through to time is used to estimate fracture property. The log plot, as we've already seen how to do that. First thing we have wellbore storage, which gives us this unit slope line from which we can orient ourselves to where the end of wellbore storage domination is. We then have the linear flow and bilinear flow, which are 1/2 and 1/4 slope lines with regard to pressure drop and time. And then we start talking about, of course, they're giving it to us in dimensional form, but the derivative gives us a constant value on the log plot. I'm going to ignore the second infinite acting flow region because that's for dual porosity systems. And then there's single no flow boundary, which is a fault. That'll give you that signature. The slope will actually double. And then boundary dominated flow. We're back to the same thing that we had up here for log. Now the question is, for the wellbore storage. Why is wellbore storage? Okay, so we have a tank like this that's the wellbore, and we have a perfect pump that's taking fluid out of the wellbore. Put a perfect pump on here, so it's doing it at a constant rate. And inside of this, we have a green liquid. This could be Jeffrey fluid, okay? So it's coming out here, the green liquid is, and the rate is constant, so Q is equal to constant. Okay? Now, tell me, class, what is the height of this column of green liquid going to look like as a function of time?
Exponential, okay?
Slow down. Minute?
So start linear and decrease.
No, it will totally be linear because the rate is constant. Correct?
Yeah.
Okay, so the height will decline with time, like that. At time 0, you okay, sir?
I can't believe I got that wrong.
Yeah, well, it's kind of a trick question, you know. Okay, so this is H at T equals 0, and then whenever the tank's completely empty. So what happens when you take the pressure drop relative to H at T equals 0? If I then calculate delta H, the delta H is going to be H0, which is this, minus HT. What's that going to look like when I plot it on a log grid?
Straight line?
Okay, so that'll be delta H versus T. And what's it going to look like? It's going to be a straight line like this. What's the slope? It's going to be 1 to 1. And so there's where the unit slope concept comes from. All right? So if we had a system, it could be, we're talking about a fluid level with a perfect pump that keeps a constant rate, and we withdraw it. It's a cylinder, okay? It's not funny shapes or something like that. Then what will happen is the rate of decline will be linear, and then when we flip it and we solve it as H0 minus HP, it'll give us this on a log grid. Now, this is a tank of water, it does not have a radial flow region, right? It's just a tank of water. That explains the wellbore storage part. Somebody now explain the pseudo-steady state part. All of this rhetoric has been to explain this. Okay? But this is identical to that. Yes, no, maybe?
But the derivative on the,
Okay, let me try this, okay? Stop guessing, G. I'm really enjoying this part of the game, by the way. How do I turn ink off? You ready, Jeffrey? I'm feeling good? All right. So what I'm going to do, and then I think I'm going to quit because I'm exhausted. So I'm going to explain this wellbore storage thingy one more time. You guys want to use Microsoft Ink so we have more colors?
Yep.
Color, color, color. All right? You ready? So we have our tank over here. Why is it green? All right, it's green. Green tank. Everybody likes a green tank, right? Oh, they like a blue tank. All right, so we have a tank over here. And it's full of green stuff. What's that green stuff called?
Jeffrey's wood.
It's called oil. Okay. So we have a perfect pump. We have a pump with a raised constant. Okay. Comes out like that. The height here this is H0. Okay. And of course this would be 0 down here. So we're going to look at this fluid height just like we did before. Is everybody comfortable with this so far? Okay, so if we plot H of T versus T, what's that going to look like? Jeffrey, we're going to give you a redemption piece here. Here's H0. Okay? Now what's going to happen?
Straight line with slope of negative. Negative.
I don't know what it is because we didn't specify a model. Okay? But this is H of T. Now I want to plot a log-log plot. And on the log-log plot, what am I going to plot? Plot H0 minus H of T and then T. Okay. Everybody's fine so far, I hope, right? Okay, so it's the same thing over again. We're going to have a unit slope trend. Okay? And that's for the wellbore. Okay? Everybody happy? And what if I take a tank that's a reservoir and I fill it with a constant compressibility fluid? Does anybody remember the equation for that? material balance equation. It's P bar is equal to PI minus what? 1 over NCT, sorry, minus, not equal. VO over VOI times what? Didn't you guys already have 665 with McCain?
Yeah, not with the king.
Well, with the clan of K Fair. I mean, you guys never saw this equation before?
Yeah. But
Where?
665.
In 665. All right. So we'll rewrite this equation. We'll say it's P bar is equal to PI minus M pseudo steady state times what? All right. NP is equal to the integral of Q of T dt. If Q is constant, then what is NP? Dennis? NP is equal to Q times T. So we're going to say constant rate, and that'll be what? So I'm going to take this out. Let's say 1 over NCT, VO over VOI, Q times T. Okay? Say Q constant. All right? What's the last one? PI minus some constant M pseudo steady state times T, right? All right? What is PI minus P bar going to be? M pseudo steady state times T. Okay. But we don't usually work in terms of P bar, do we? What do we usually work in terms of? PWF. Okay, so we need another equation. Anybody got another equation in their pocket? So we need P bar minus PWS, F, pardon me. Yeah, I know. We don't have to write delta for this. So P bar minus PWF is equal to what? We already saw this, B pseudo steady state times Q. Okay. So now what do we do?
Substituted for P bar. Substituted for P bar.
I can't do it.
Substitute for P bar.
Okay, and what's that going to give us?
PWS. Right.
What's it going to give us?
Give us an equation which will deal with the drawdown Pi minus PWS.
Okay, what happens if Q is constant? Okay, so you want to just go ahead and combine these two right now, right? But we've already said Q is constant. So we may as well go on ahead and define this as B pseudo steady state star, right?
Okay.
So now what's it going to be? It's going to be PI is equal to PWF plus
B star.
Okay. Is that the way we want to write it? Let me write all the steps out so I don't get confused either. So that means P bar is going to be equal to B pseudo steady state star plus PWF, right?
Yeah.
And when we substitute that in, what do we get? We get PI minus, outgoing right that way, PWF, minus B pseudo-steady state star equals M pseudo-steady state times T. Okay, so that means that PI minus, or we don't do it that way. My mistake. It's PWF equal PI minus what? M pseudo-steady state. And then plus?
No, minus. B. And you're missing a T. Yeah.
Shut up. Everybody's crazy. All right? What did we do wrong? Nothing. Because now we got a PI minus B pseudo-steady state star quantity minus M pseudo-steady state times T, right? What do you want to call that? We can call this P pseudo-steady state star. Something like that. Give me a name. Think up something. In the end, it's going to be PWF is equal to alpha minus beta T, right? Is that correct? So, this is a tank, a reservoir of oil in the ground. Sounds like a Michael Jackson song. What a tank in the ground. Okay. This is the equation for that. PWF is equal to alpha minus beta times T. Okay? Dennis, is that the same as everything else?
Yeah.
Yeah. So we could have alpha minus PWF is equal to beta T. Okay? I guess we could cut out the middleman and call this P0 or something. We'll call alpha P0. You guys like calling it P0? Okay. So now we have P0 minus PWF is equal to M pseudo-steady state times T. So it's exactly the same formulation, right? So what's it going to look like on a graph?
The slope on it, steady state.
We have T0 I hate these things. I wonder if maybe one of you guys can invent a better one. And please don't tell me that every bad carpenter blames their tools. I know that's what somebody's thinking out there. But don't do it. I just did this wrong. Why didn't you let me do that, Dennis? Okay. So this is going to be, what's the slope of this? M pseudo-steady state. And P0. Comments? So what happens when I plot it on a log graph?
Then what is this different slope equal to?
The same slope. They're both in slope. Right? But it'll be out here. Comprende? reservoir. Okay? What connects them?
The volume,
Sorry?
the volume is,
The what? Sorry, I couldn't hear you.
oh, what's in the middle?
Yeah,
That would be,
that'll be the radio, the transient radio flow part.
right here.
Okay. And then this is that IARF, the infinite acting radio flow. So this tells you the volume of the wellbore. If you wanted to think about it that way. Oops, bad phone, sorry. And this tells you the volume of the reservoir. Okay. Or sorry, this is proportional to the volume of the well. This is proportional to the volume of the reservoir. Okay? So congratulations, I think we've covered just about everything humanly possible with these simplified things for today. It's impossible to teach all this material in this short of a time period. Alright, so I'm going to switch my Okay, now, getting back to something a little less tedious. Why did I put a dashed line around this and this?
Do they have a rate of not equal to 0?
Sorry?
Do they have a rate that is not equal to 0?
So does the other,
Well, these would be secondary choices. What would your primary choice be?
the buildup.
Buildup. The problem with both the injection test and the drawdown is that the rate has to be caught. Not literally, but at least directionally, it has to be caught. There are ways around the variable rate, but they're not caught. Okay. So from a drawdown test, we can estimate reservoir behavior, permeability, skin factor, pressure half length, reservoir limits, boundaries, and we could also do horizontal well features, pressure conductivity, etc. Follow-up test, they claim you can do mobility. I'm not sure about that. Skin, pressure again, fracture again, location of front again, boundaries, location of front, and reservoir limits to be sort of the same thing. Now we come over here to build-up test, and they get reservoir behavior, permeability, skin, fracture length, reservoir pressure, and boundaries identical to the drawdown test. But our preference is going to be the build-up test. It's just sort of a diagram or a listing.
What is the reservoir limit?
The reservoir limit test would be where you're going to this part. That's your reservoir limit. We're talking about infinite acting radio flow here. This is boundary effect. Sorry, I'll go ahead and label that for you. This is boundary effect. Reservoir. Boundary effect. Okay? This is another sequence of plots. This was sort of an early effort, or maybe I should say a late effort. This was done in, what, 1983? No, 85. What Rashagi and Woodbury were trying to do was trying to show characteristic shapes. At about the same time, people were trying to start doing artificial intelligence on well test analyses. Let me rephrase this. There was a tool to to do this. But then the models kept getting successfully more complicated, and I don't know whether that tool was maintained or not. It came out of a group at Stanford. It's in the Kappa software suite, or it was. But what Oshagi and Woodbury were trying to do is they were trying to show certain flow regimes and how they behave. Wellbore storage is a straight line on a log-log plot. We already know that. We've already been working with that. Infinite acting radial flow is a straight line on a semi-log plot. So this is a check mark. This is a check mark. We already studied both of these. And then we have formation linear flow, which may not seem logical, but this is going to be 2 to 1. Okay? And if this is 2 to 1, then that dictates that square root. I am not a fan of square root and quarter root plots. Do you know why? Okay, so you notice what he did is he plotted the square root here. He took this data, I mean these are cartoons of course, but it implies that all of the data here are square root. They're not. Real data doesn't look like this. Real data over here will have sort of a tail like this and then it will tail off like that. What does it look like when you plot it versus square root? It still kind of looks like this and like that. So it makes you think that the whole thing is square root. I understand. I am an anomaly. I have some very serious, vision difficulties with using these kind of plots. I would much prefer that you use the log-log plot over here. You can still see it. I'm sorry, I can't believe I just did that. Scratch, I want a mulligan, do over, whatever. You can still see the features. Okay? Using the log-log plot. Better to use derivatives, what we did. So the next slide is going to be derivatives, if I remember correctly. And I do. This is something I had my graduate student draw up. This is incorrect. Sorry about that. Oops. Sorry, wrong reference. Actually, they may have done this, but we enhanced it. This is from a student of mine. And what we're looking at is an unfractured well and homogeneous infinite acting reservoir, which is radial flow. And you can see the logarithm of dimensionless pressure has a hockey stick shape. There's your 1 to 1, and then it rolls over. And then we look at the logarithm of dimensionless pressure derivative, and it has a hump, just like expected. And then we look at the logarithm of the beta derivative. The beta derivative is the derivative divided by the pressure drop. And what that tells us is that during wellbore storage, we get a unit slope line here and here, and that translates to a horizontal behavior here. So this was sort of a diagnostic that we were trying to put out there to get everybody to realize this was constant because it was dictated by this formulation. The next is about an homogeneous, an unfractured well, again, radial flow. Does everybody see what we saw a moment ago? Here is your wellbore storage trend. So this is wellbore storage, and this is your reservoir trend. Okay, so that's what we just drew on the other graph. So here you're looking at the volume of the wellbore, and here you're looking at the volume of the reservoir. The derivative echoes the same thing, just like I drew earlier, so we still have the straight line unit slope trend, straight line unit slope trend, and then some differential in between that transition. This is what, Jeffrey? This is infinite acting radial flow, right? And the next is with a sealing fault. You can see that here. Okay, and I guess the best thing to remember is, although this is a little bit ambiguous, This is not. This is a fixed point in space. This is for the ceiling fault case. Okay. And then when we have a fractured well, infinite connectivity vertical fracture, finite connectivity vertical fracture. So this one is infinite connectivity. This one is finite connectivity. Okay. Take their derivative, infinite connectivity, finite connectivity. You see they look very similar. Why do they look very similar? From derivative to pressure. Because they're both governed by the same equation. Quarter slope on derivative is going to be quarter slope on pressure. Quarter slope on pressure, or sorry, half slope on pressure is going to be half slope on derivative. And I'll leave that alone. We won't go into any of this anymore. But I think you see what I'm trying to get at. These are learning the various characteristic shapes and behaviors. Questions, comments, insults, thoughts?
In the second one, the middle part corresponds to IARF, right? But
This?
yeah.
And so does this. Sorry, I didn't draw it in.
Why does the log of the P, the other P,
Sorry?
why does the third row, it doesn't look as if it's constant?
Because the, what happens is there's a slight transition.
So
I mean, it's a great question. I'm struggling to answer it because I don't want to say something stupid, but it should be flatter, I believe. Let me see. No, sorry. For radial flow,
second column, third row.
no, the radial flow is a derivative.
Even if
No, the beta derivative will not be a constant. The beta derivative is delta P prime over delta P, right? So if it's constant, if delta P prime is constant, then delta P is going to pull it down. Okay? Like this. The only place this is going to be 1 is here during wellbore storage, and here during boundary dominated flow. Here and here. Alright? Thank you. Great question. Sorry I had to pause and reflect on that. The reason we defined the beta derivative function was to take care of regimes which were not radial flow. Thanks for reminding. Alright, let's see what our next slide is. And as we close this part of the discussion, what are some of the practical challenges? You just saw that identification of the appropriate reservoir model, which means pick the right model from the diagnostics that you see. There are artifacts in the data. That is, when you have a data function which has got some error in it, or data function which is corrupted by a producing time effect or that sort of thing, that could be, you can end up analyzing an artifact which is a shadow or a residual of something else. Estimation of reservoir properties is really going to depend on the quality and quantity of the data. What are the diagnostics? We have something called conventional plots. The conventional plots are log-log, semi-log, Cartesian, and some of the, I guess you call it, square root plots. And then we have the diagnostic plots, which are primarily log-log plots of derivative and the integral function, and you saw that a moment ago. We do not use integral functions for well test analysis much. It just didn't catch on. Who invented the telephone?
Alexander Graham Bell.
Are you sure? What do they teach in Thailand? Who invented the telephone?
no, it's the same.
Are you sure?
Edison or Nikola Tesla might have.
So when I did this in my 620 class 20 years ago, I had a Russian, and he goes, everybody say Bell did, but he stole it from Dombrowski. Okay, so that happens, right? I mean, people think that somebody else invented something. Wasn't there a guy named Gray who invented the telephone as well? And Bell got to the patent office before he did. There's also been some Italian, right, that supposedly invented the telephone. You know, sorry?
Marconi?
No, it was just some obscure, you know, people were, I mean, look, you follow the same paths, you sniff the same ground, you're gonna derive the same thing, okay? So in 1989, there were 3 papers at a conference, and they were all on the so-called pressure integral method. And I can assure you, none of those people communicated with each other. It was a shock, okay? And I was one of them. So that was a very, very unusual moment. But people were working, trying to figure out new diagnostics and everything else. So I wrote this paper called the pressure integral method, and somebody else wrote another paper, and somebody else wrote another paper. All right. Why would you use an integral formulation rather than a derivative formulation? Give me one good reason. Give me no good reason. What does a derivative do?
It gets rid of data.
Explain.
Any constants and anything.
Okay, so it'll take something that has a constant in it and remove it. But I'm talking about
By that logic.
continuous functions or some sort of a distribution of data, what the derivative is going to do.
Find the rate of change.
Sorry?
Find the rate of change of the
Okay.
function.
It's gonna add them up.
The derivative?
Oh, sorry, wait.
Okay.
What was your-
Bring the duct tape on. Anybody else want to comment? Why do we take the derivative of something?
People give you the maximum minimum.
Good idea. Do you know that one of the guys who claimed to invent the pressure derivative worked for Schlumberger, and that's why he said he did it? He was looking for gauge drift error, and that he programmed a derivative algorithm. He was a wireline engineer, and he was looking for the gauge drift error and was using that. Also seen a guy from another university claim he invented it. You know, this has been around. You don't invent something. You know, it's just been around. It's laying around. It's mathematics. But why would you use a derivative? Think carefully. You said to remove constants, but what I think you really meant was to show the underlying rate of change, which will have more resolution than the function itself. If you take the derivative of a function, it has more character, more wiggles, more something. On a rare occasion, it might even have a constant value or some sort of behavior like that. So the derivative turned out to be a really powerful solution. It was able, you know, we were able to do what we just saw in the previous graph, which is characterize flow regimes and do that. Okay, so why would you define a pressure integral function? If the derivative already did all the things you wanted done, why would you define a derivative or an integral function? Yes.
We have a lot of errors in our pressure that are
Keep going.
so
Getting
when
warmer.
you add them all up, you get it smooths out the error. At least that's what I.
Okay. I'd say he's in the right place, but got there from the wrong way. So go ahead, Abdallah.
So let's say the derivative of a cloud is a bigger cloud in terms of error, so when you integrate it, you see a more
Correct.
big picture.
It will smooth or condense the data. Okay? What's the problem with that? Well, the derivative, when you're looking for rate of change, all right, let's say you're taking the derivative of a path up a hill. When you take the derivative, the second things change, the derivative is going to pick that up. All right? But let's say instead you're taking the integral. The integral is going to smooth that out. It's going to blur that. It's going to delay that feature. And that's one of the problems with the integral function. That was one of the big criticisms. It worked exactly like you implied. It took a noisy data set and made a nice, smooth data set out of it. Analysis was good, interpretations were good, and so forth. But it smeared the data. And for some reason, it just never caught on. Okay. So as a prelude to Monday, when we talk about production data analysis, I want you to think about this. And we may cover some more of this. I have it in my back of my mind to do some more on this. But what would the integral do for you for production data? There it doesn't matter because you have a huge history. So using the integral for production data is probably a pretty good idea. So just like somebody who invented a can opener that later turned out to be a pretty good putty knife or something, that's what I did. I used the integral functions for production data analysis, and sort of the rest is history. Okay. But the key here, conventional plots, log, semi-log, Cartesian, root time plots, those need to be made, but they need to be coordinated. When you start using software, you guys used software before in your other class? No? You did? In the undergrad?
Well testing?
Yeah.
Oh, yeah.
Yes. Okay, so you used Paquette. How did that work? You threw up a log plot, and they have a line that you can manipulate, and you put that on part of the data, and up pops the permeability number, up pops the skin factor number, all that, right?
You just click.
Yeah, okay, you just click. I'm not real sure I like that, but okay. So, the Kappa product line doesn't do that. The way they work is you're looking at diagnostic plots, similar to Paquette, but instead you drag a line to it, and you calibrate off that line. But the whole point in Kappa is to calibrate the model to the data. The point in Paquette is still somewhat about analysis, getting a piece of the data to agree with something. They store that value, and then when you run a simulation, it picks it up and puts it through the data. Ironically, and I realize this is being recorded, it appears, at least in the last time I used it, which was a couple of years ago, that WellTest actually had a bit more robust regression algorithm than Sapphire did. But, in fairness, and I'm not trying to play favorites on either one, the model in Sapphire is much more complicated. So it probably had a struggle in doing those regressions because of the complexity of the model. But, so whenever you leave this course, chances are you will never ever do another analysis by hand. So you need to be aware that software is evil. Software, it lures you into believing you know what you're doing. Sorry, what was it again? Just click here? Just click here. That's what the software does for you.
But you can, they do give you the raw, enough data set where you can just do a quick diagnostic plot.
And
for yourself.
Yes.
See for yourself.
Yeah. Yeah. Both of them do that. There was another product called Pan System, which was before that. Pan System's still sold by Weatherford. I don't know that it's maintained as much as it used to be. It was a fantastic tool when it came out. I mean, you guys have no idea how fortunate you are. You'd have to plot this stupid data by hand. You have to, we didn't have the derivatives. You had to do all these lines and everything else, and make slopes and intercepts. But Pan System just blew all that away. It really was a nice package. It had some quirks. I think it was mostly developer quirks. They like to look at data in a certain way, but Pan System, from what I can tell, is pretty much fallen off the chart. But maybe not. Maybe they're going to listen to me and then they'll come roaring back. I think what I'm going to do is get this part. You're responsible for it, but I want you to, it's not going to be something you're going to be tested on. All right, what about pressure distribution? Why do we use pressure distribution? Why do we learn these equations? Why do we calculate things in terms of radius?
Because pressure difference governs the fluid
Sorry?
flow. Pressure difference governs fluid flow.
Okay, but why do we look at places other than the wellbore? We can't measure the pressure there.
Although we measure the pressure at the wellbore, the time that the pressure responds to it can actually be correlated.
What are you really trying to say?
The radius
You're
of-
saying that I can't measure pressure out in the reservoir, but I can calculate it. That's what you're really trying to say, if you want me to be your puppet master. Okay. So we have to learn these equations. What we're looking at is a steady state solution, which actually we already derived today from Darcy's law, and then we're looking at the full solution. The nice thing about the steady state solution is it tells us what's the behavior of pressure with respect to radius. It's logarithmically scaled. Here, The pressure in the reservoir is equal to the pressure in the wellbore plus a constant multiplied by a logarithmic ratio. So the pressure distribution during steady state is logarithmic. It's just something that happens. Okay? The full solution, and Dennis, do you remember this? Yes. Okay, we have the first term, which is the transient flow term. We have the second term, which is at the outer boundary. We have a material balance term here, and we have a transition term there. Why did I make you learn all this, Dennis? Who cares about a radial reservoir with a hole in the middle? Is that really the engineer's favorite tool? Well, it's a favorite sort of starting point. Okay? So what we really want to know is, what do these distributions look like? Jeffrey, for an A in this course, and if you break my snake, my French curve, okay, you'll get to eat every piece of it. Okay. This is a diagram of a drawdown pressure profile in a bounded, or well, actually it's an unbounded radial system. The solid lines are the pressure distributions at a given time. Here's pressure, here's distance. At 0.1 hour, this is the pressure distribution. At 1 hour, there's the pressure distribution. At 10 hours, and so on. Are these straight lines?
No.
No. Pseudo straight?
They're straight until the end.
Very good, Joe.
Then they hit, I guess, the end of their pseudo state.
No, this is steady state.
Oh.
Or appears, these are actually transient, but they appear to be steady state inside. Don't break my French curve. You'll be eating it. Okay, so anybody want to tell me what these intercepts are? What is this? What is this? What is this? What is this?
The radius of investigation.
Okay, and what is the radius of investigation?
Where most of the pressure drop happens. So between it's the distance.
Looking at this graph, what's the radius of investigation?
It's where.
Think first, speak later. This is initial pressure here. 2,000 psi.
It's the edge of the pressure.
We had a breakthrough. So it is a fictitious intercept of the steady state distribution with initial pressure. That's the definition. So this point, that point, that point, that point are the blue models extrapolated until they hit the red. Red is good. Red is coming. Right? Little joke. Don't worry. I'm not calling you a communist yet. Actually, probably pretty good to be communist nowadays. All right. So here's the definition of the radius investigation. Anybody want to know how that was derived?
Through the gamma function.
Is it not through the steady
Take
state?
a deep breath. Jeffrey, go ahead. That's all.
Oh, is it not a steady, not from the steady state solution?
What it is, what it was, and what it shall be is a straight line overlaying onto here. It's a steady state distribution from here overlaying onto the data there. Okay? Just a straight line is a logarithmic relationship. You guys really want to derive this? No, where's this from? Okay, I guess we'll do it anyway. Where's the sniffer? What's the sniffing tool under?
We just type it.
Hmm?
We just type it there.
On the command line? Here?
Yeah.
Snip? pretty smart. I wouldn't have thought of that. Shut up, good stuff, honey.
You could just go to the layout and select blank slide.
Yeah, I could go start drinking again. Yeah, I know. You're telling me. All because of you. Much. Alright, so the definition of dimensionless pressure for this case is PD is equal to 1/2 natural log 4 over e to the gamma RD squared over 4TD. I believe that's right. No, over TD. Hey, Cindy, say it forward. Okay? So, what is the equivalency of that straight line? Hello? Would you two girls stop fighting? So in this graph, it's not obvious, but what I'm going to do is I'm going to solve this equation. So that's equal to 1/2 natural log, well, let's say that this is equal to 0. Ready? So we're going to say that PI equals, is it P, doesn't it? Yeah. I can't believe I just did that, sorry. I'm really sorry. Alright, so P of RT is equal to PI, therefore PD is equal to 0. What is 0 multiplied by 2, Dennis?
0.
And 0 is equal to 1/2 over e to the gamma RD squared over 4TD. Stop writing 4. Okay, so 2 times that is? That's still 0. Okay. So that's natural log 4 over e to the gamma. Anybody got any ideas how to break this up?
1 equal to 4 again.
So that's equal to, well, you don't have to go that far. EXP of 0 What is EXP of 0? 1. Did I just do that? I cannot believe it.
How did it start? Yeah.
I know. I'm sorry. I'm just too tired, sorry. So that's equal to 1, and that's equal to 4 over e to the gamma RD squared over 4.
Over 80.
Right, 4 times. Is it 4 TD?
Yeah, I think it's good.
Or the 4 we can't double that.
No, not that. I think I got it upside down. let's just see where it goes. Okay, so we wanna solve this, that's gonna be,
You forgot the half, I think.
no, the half's gone, the half went here. That's e to the gamma over 4 TD equals RD squared. So RD is equal to square root e to the gamma over 4 square root TD. I think I've got this upside down. I think it's that's 4 over e to the gamma. Sorry.
No, it's T over R T plus.
Yeah.
Yeah.
Exactly the reciprocal of what you wrote.
Sorry?
The whole term that you wrote over there is the reciprocal of what it should be.
Shut up. I really screwed that up. Just for that, you made me do it over again. Alright, so what we're gonna say is that PD is gonna be equal to 0, alright? The line's gonna intersect, okay? So what happens, if that's equal to 0, then all of this is 1/2 times that quantity. So what's that gonna be?
Zero is equal to the quantity. Basically, the term in the bracket is equal to 1.
Okay. So that tells us that 4 over e to the gamma, ed over RD squared is equal to 1. Okay. So that means RD squared is equal to
4 over e to the gamma.
4 over e to the gamma, ed, and that's basically our starting point. That means RD is equal to square root 4 over e to the gamma, square root TD. What's RD? RD is equal to R over RW. What's TD? Dennis? 0.002637 times K over B U C T RW squared times T, right? Okay, so that's going to be R over RW. It's going to be the square root of 4 over e to the gamma. And all of this will factor out except the square root of TD. But I'll go ahead and leave it in there. So that'll be the square root of 0.002637. Square root of K over BU CT R squared. Times square root of T. Alright? What happens to this RW? This RW and that RW squared cancel, right? So that tells us that R is equal to square root 0.0002637. Sorry, there was another 0 there. Multiplied by square root of 4 over U gamma is square root of K over B U CT square root of T. Are we close?
Well, you just need to factor it in the
Okay. Gamma is equal to 0.6, or sorry, gamma is 0.571. Is that, what is gamma?
0.5.
It's 0.
Euler's constant, right?
It's gamma, Euler's constant, 0.571266 or something like that. E to the gamma is 1.781. Okay. So what if all these numbers equal whenever we work them out?
It equals to 2.4.
Okay, so we have, not anymore, square root of 0.000237 times the square root, or times 2.
You have 8.
Yeah, I got it. Times the square root of 1 over 1.71. And that is the same number. Okay? So there's your proof. That's how we get that number. We take this equation and derive it. So I got 0.02434. Let's check something. That's one definition of the radius of investigation. Now, why are there other curves on there? Oh, geez, the thing's gonna stop, the recording, we gotta stop, it was only good for 3 hours.
Oh, you said 4.
He came to me and said they couldn't do 4.
So,
Well, that's good, the best part, we lopped off. Okay, well, I'll keep talking, and you guys will get the gist of this. This is the build-up portion, so these are the recovering build-ups, okay? So what happens is you produce it down to here, and then when you shut it in, this is the recovery of 0.1 hour, 1 hour, 10 hours, etc. What do you notice? Okay, so think about it this way. These curves, that's at 0.1 hours, 1 hour. Bring me a bigger thing. I've actually got a bigger one. All right? So what happens is, why is the distribution flat here? And then the next one's flat.
What does the PVCU stand for? What is the PVC?
CD is drawdown, BU is buildup.
Okay.
because there's no flow, so there's no,
Louder, sorry.
no flow, so it's assumed constant pressure.
It's not exactly, but in a way, what happens is, imagine at extremely small time, down here, it would do this. It's always gonna come back to this line, because that's the drawdown line. That's where we stop. And it's gonna keep walking up. Okay? What happens is the pressure level builds up across that part. And then at the next step, it builds up another step. And the next step, it builds up another step. It's a logarithmic scale, so it might be a little bit confusing. But essentially what it tells you is that the pressure during a buildup is not a function of distance, it's a function of time. Does everybody understand that? For the moment, it's meaningless, but it has value later on, and because it allows us to use pseudotime. Pseudotime should be an integral of the reservoir pressure profile, but if the reservoir pressure profile, okay, so you'll notice it also reverses back the same sort of intercept as well. So you were saying earlier that there's a finite speed of propagation. The speed during the buildup is the same as the speed during the drawdown. So it should end up back at the same place. So the radius investigation during the drawdown, that makes sense, we just derived that. But the radius investigation during the buildup is the mirror image of that. Okay. I have reserved, I don't know what time. I asked Ted to reserve it on Sunday afternoon. Do you guys want to meet again on Sunday afternoon to complete this, or no, nobody does? I guess I'll do it alone. I'll send a note, and if you want to come, you can.
How exactly do we use this one?
This is more of a diagram that's explaining a map of what the pressure profile of the reservoir looks like. This one's very simple. This is what Lee had in his textbook. It just shows that equation plotted as a function of position. But what I added to it was the buildup. So I took this particular scenario and I drew those lines on there and I added a case of 1,000 hours. And then I came back in and I shut it in. I turned the solution off and then looked at what the pressure profile was going to be. So what I want you to focus on is that you have a steady state pressure profile moving through the reservoir during drawdown. It's not exactly steady state because only the straight line portions correspond to the steady state part. And like you were implying, Jeffrey, it extrapolates to touch PI, but it can't do that in reality. It has to turn over. And where it gets that turnover from is in these exponential integral terms. That's where it gets the turnover. Okay? Well, all righty then. I think we got to stop because we're going over the tape. I honestly don't know what he said it for, but he said he didn't want to go much over 3 hours. So.
Anybody got any change for a 5?
Yeah, I can change it from your hand to mine. Why didn't you change for a 5?
Yeah, go ahead now.
I don't know anything. Thanks again, everyone. I know this is slow and kind of dragged on. The theory is important. The other 10? The other 8?
If you want to, outside. Never do that to Schubert though, because he will assign where.
Do what?
Ask him about it.
Sam was saying, hey, you wanna ask about an assignment, and Dr. Sealer and.
No, I will absolutely give you an assignment if
Yeah.
you ask me for
Yeah,
one.
no, but that's what Dr. Sealer does, too.
Dennis, you like your assignment?
Oh, absolutely. I love not having another week or two. I love not having weeks to do anything besides assignments.
Good. I like your way of thinking.
Pretty messed up, man.
Kind of funny, although that guy must have liked it.
What's
I
that?
think I spent like 60.
This is what we got. I got some, I'm confused today. I gave him $8 in cash. Almost said I wrote in $8 for tip on the credit card. Yeah.
Remind me to never let you handle money.
I'm usually better.
You gotta wait till dark. And then you turn into a permit.
Sorry?
And then you turn into a permit.
Exactly.
So would I have love on Monday?
Sorry?
I would have love on Monday?
I gotta figure, I don't remember what time he did it,
Okay.
because I gotta go check my email. I don't know what time he set it up, but I'll send a note to say, see, I was gonna hold it and see how far we got today, but, I'll make a decision. It may be Sunday before I send it, so. I've got two really big things to do this weekend and a whole bunch of really small ones.
Can you help Sam, though?
No.
Can you leave now?
I'm good.